Hi everyone, welcome. Today I am presenting our analysis of a two-dimensional truss structure. We used the finite element methods for this project, which was part of our finite element method course. My name is Oğuzhan Pekacar and I collaborated with my colleague Mustafa Tupal on this project. Our primary goal was to develop our own FEM code from scratch to analyze this to this truss. We aim to accurately calculate the displacement of each point in the truss under applied forces, the forces on the supports holding the truss, and the stress which each truss member. To ensure the accuracy of our code, we compared our results with tools from Abaqus, a well-established FEM software. This comparison helped us check the accuracy and efficiency of our solution. For this project, we need to present the actual FEM notes we wrote for analysis to the trusses, the results from our code and their comparison to Abaqus, a detailed report with visuals of the truss before and after applying forces, and a plot showing the stress distribution throughout the truss. The structure we analyzed is a 2D truss similar to a bridge or crane made of straight bars connected at joints called nodes. When loads are applied to this truss, these bars either stretch or compress. We were particularly interested in determining the horizontal and vertical displacement of each node, the forces the supports must exert to keep the truss in place, the stress each bar in the truss experiences. To better understand this, we created visualizations of the truss before and after applying loads and generated a color code plot showing the stress distribution across the truss. We followed a 5 steps process for this project. We developed our own FEM code to solve the 2D truss problem. We modeled the same truss in Abaqus to benchmark our results. We compared the results from our code with the Abaqus results, focusing on nodal displacements, member stress, R, and reaction forces. We created visualizations of truss before and after applying loads, including a stress contour plot to show the stress distribution. We evaluated our code's performance in terms of accuracy, efficiency, and ability to manage trusses of different size and complexity. Our first major task was to write the FEM code. Here is how to approach it. We calculate the element stiffness matrix for each bar in the truss. This matrix describes the stiffness of each bar and depends on factors like its length, orientation, cross-section area, and material. We combine these individual stiffness matrices into the global stiffness matrix for the entire truss. We applied boundary conditions to the codes specific which nodes are fixed, which is essential for a meaningful solution. Using the global stiffness matrix and the applied external force, we calculate the displacement of each node. Finally, we use these displacements to determine the reaction force at the supports and the stress in each member. To validate our work, we built the same truss in Abaqus. This allowed us to compare our results for the displacement of each node in the x and y direction, the reaction force at the support, stress in each truss member. Comparing our results to Abaqus give us confidence in the accuracy of our code. When comparing our code's results with Abaqus, we focused on 3 main aspects: nodal displacement, reaction forces, and axial stress. Firstly, nodal displacement. Both methods gave comparable results for nodal displacement. The largest difference was less than 2%. Interestingly, node 4 moved the most both the x and y directions in the both models. Reaction force, the force at the supports were also very consistent between the two methods, indicating correct application of boundary condition in our code. Excess stress in the truss members were also close between the two methods, with a maximum difference of about 1.2%. Any small differences are likely due to slight variation in how the two solvers manage numerical calculation. Here we see two images of the truss. The first shows truss in its original shapes before applying loads. The second shows how the truss deforms under the applied loads. We also created the color code plot called a stress control plot. Stress distribution throughout the truss with red areas experting high stress and blue areas experting low stress. Let's dive deeper into the how we implement our fifth FEM solution in MATLAB. The core steps included we created element stiffness matrix for each bar in truss. This matrix describes each bar resistance to stretching or compression. We assembled these individual matrices into the larger global stiffness matrix representing the overall stiffness of the entire truss structure. We applied boundary condition to tell the program which points on the truss are fixed, which is critical for accurate calculation. With this global stiffness matrix and the external force, we calculated how much each node connection point in the truss would move. Finally, we used these calculate moves to determine the forces at the supports and this stress each bar experiences. Our MATLAB code was quite efficient for trusses that weren't overly complex and gave us accurate results. However, we realized that with larger or more intricate truss, we might encounter stability issues or longer computation times. We can address this in the future by optimizing the code and using better numerical techniques. This slight displacement in MATLAB code we developed for the 2D truss analysis. As you can see, it is quite concise and well trusted. We will delve into the upcoming slides. Here is breakdown of this part of the MATLAB code. In defining active parts is the code first identify which parts of the truss are free to move and assign them special numbers. Applied loads it defines an external force applied to specific points on the truss. Wielding the stiffness matrix, the code creates a mathematical representation of the entire truss resistance to deformation by combining the stiffness of each individual bar. Creating the force vector, it creates a list represents all the external force acting on the truss. And this section of the code, gathering displacements, the code collects and organizes the calculated move of each node, connection points on the truss. Calculated force and stress for each bar calculates the external force and stress, telling us about the force within each bar and its distribution over the bar cross-section area. Preparing for reaction calculation, it sets of necessary tools to calculate the forces at the supports need to keep the truss from moving. Moving on this part of the code, calculating reaction force, the code calculations the forces at each support point at the supports exert to keep the truss stable under the applied loads. Displaying results, finally the code presents all the results clearly, including the movement of each point, the forces within each bar, the stress each bar, and reaction force at the supports. Now let's look at some specific function with the code truss TI. This function calculates the angle of specific bar in the truss, telling us its orientation. Truss GI, this function determines which degrees of freedom are associated with particular bar. Degrees of freedom refer to the ways a bar can move, such as horizontal and vertical. Truss KLI, this function calculates the stiffness of an individual bar in the truss, telling us how much it results deformation when a force is applied. There are MATLAB function definition form truss F. This function creates a list of all external force action on truss structure. Form K, this function combines the stiffness of all the individual bar to determine the overall stiffness of the entire truss. Print truss results, the function neatly displayed all the results of our analysis, such as the movement of each point and the forces in each bar. A couple more important functions, calculate the reaction force. This part of the calculate the forces needed each support point to keep the truss from moving under the applied loads. Calculate member force and stress. This part determines if each bar in the truss is being stretched, tension, or compressed, and then calculates the force and how that force is distributed within the bar stress.
Hello, I am Mozafari. I will continue the presentation. Now I will talk about the undeformed truss structure. The image displays an undeformed truss structure modeling on Abaqus. Truss structure is structural design designed to support the loads through interconnected triangular elements. The green lines represent the structural members. Also, it's a 2D coordinate system, X and Y. Now I will show the deformed truss structure. This image shows the deformed state of the truss structure after applying external force or loads. The green lines represent the structural member in their displaced points. Also, the deformation indicates how the structure responds to the applied load, highlighting areas of displacement and structural behavior under stress. Now I will talk about the U displacement, U1 displacement. This image represents the U1 displacement result of the truss structure analyzed in Abaqus. U1 indicates the displacement along the x-axis, showing how far each node or point has shifted horizontally under applied loads. The color gradients from blue to red illustrates the magnitude of the displacement. Blue region minimal displacement, red region maximum displacement. U1 displacement. And now I will talk about the U2 displacement. This slide shows the U2 displacement distribution of the truss system obtained from an Abaqus simulation. The color legend on the left indicates displacement magnitude, with red representing minimal movement and blue representing maximum displacement in the y direction. Now I will talk about the RF1 reaction force. This slide illustrates the RF1 reaction force at the support points of the truss system. The color-coded legend of the left represents the magnitude of the reaction force, with red indicating higher magnitudes and blue indicating lower ones. It's a X direction. Now I will talk about the RF2 reaction force. Slide depicts the RF2 reaction force in the Y direction for the analyzed truss structure. The color gradient on the left indicates the force magnitude at the various support nodes, with red representing the largest force and blue represents zero or minimal force. Next slide, I will talk about the stress of member. The image shows the stress distribution in truss-like structure analyzed in Abaqus. The stress range from minus 852.6 is a compression in blue point to 8,052.6 tension red. Members with red orange colors are under high tensile stress, with blue purple members are in compression. Now I will talk about the Abaqus simulation. I will show the Abaqus simulation. It's our simulation. Now I will talk about Abaqus and MATLAB comparison. We have three parts: nodal displacement, reaction force, member force, and stress. Nodal displacement, we have similar displacement with node 4 nodes showing the highest displacement. Difference were minimal and with acceptable limits. Reaction force at fixed supports were consistent with minor differences attributed to rounding or solver differences. Member and stresses, both solver identified the same members under maximum tension and compression with small variation due to calculation methods. Now I will talk about the nodal displacement on MATLAB and Abaqus. Both solvers show similar trends, with node 4 exhibiting the highest displacement in the y direction. MATLAB results are rounded to 5 decimal place, while Abaqus uses scientific notation for higher precision. Also accuracy, despite the slight differences, the results align well. Validation, the MATLAB got reliability for displacement calculation in the 2D truss problem. Reaction force, also MATLAB and Abaqus results. Reaction force are y direction. Also, it is our stress, MATLAB and Abaqus. These slides represent comparison of a stress analysis result for a truss structure obtained using MATLAB and Abaqus. Here some key points that MATLAB results include force, stress values, and their classification as tension or compression for each truss element. Positive stress values indicate tension, while negative values indicate compression. Abaqus results the table provides the stress values each truss element is computed using Abaqus software. Comparison MATLAB and Abaqus what show due to differences in numerical method or modeling approach. The largest stress occur in the element 6 and 30 under tension, and element 4 and element 15 under compression, is seen in both MATLAB and Abaqus outputs. Conclusion, the FEM code was successfully developed and validated, demonstrating high accuracy through comparison with commercial software. It provides an efficient solution for 2D truss analyzing with potential for further refined to handle complex structure. Future work include extending the code to support 3D truss structure and improving numerical stability for large-scale problem, ensuring broader applicability and robustness. Thank you for listening. That's